Okay, hello everyone. So we are back again, okay, to review metals. Now, metals is a long chapter. And if you realize, metals has many linkages to other chapters, in particular, redox, right? Metals is very, very much interlinked with redox. So as we go through metals today and tomorrow's lesson, we need to focus and know that a lot of what we are learning in metals is intricately linked to redox, and the questions will be set as such, all right? So let's begin our study of metals. So to you, what is a metal? I'm sure you know, in the periodic table, there are metallic elements. Metallic elements in the periodic table are metals, obviously. So instead of saying metals, we can say metallic elements. Now, metallic elements are found on the left side of the periodic table. Okay, so if you look at your periodic table, the left-hand side are made of metals. On the other hand, as you go to the right side of the periodic table, it becomes non-metallic elements. In short, non-metals. Okay? So if you look on the right-hand side, you see things like fluorine, chlorine, oxygen. These are examples of non-metals. And I'm sure you already know that. Okay? But the conclusion that we can get from this is that as we go from left to right, the metallic character decreases. Right? So as you go from left to right across a period or across the periodic table, the metallic character will decrease. What that means is that the element is less and less like a metal. The element is less and less likely to be a metal. Now, up to this stage, I'm sure you have realized this. The question is, how do you explain this? How do we explain that metallic character decreases as we go from left to right across a period? Many students would think, to explain this, I just need to say, oh, metals are on the left, non-metals are on the right. But this is not explaining it. You are just repeating whatever the trend is saying. You are only saying that metals are on the left and non-metals are on the right, which means metallic character decreases. But you're not explaining why. The root cause why metallic character will decrease has to do with electrons. Remember that every single time we talk about chemistry, it's very often about electrons. Where are they located? Are they lost? Are they gained? Are they shared? Okay, so your answer, your explanation has to have electrons inside it. So now that you know that you need to explain in terms of electrons, let's think. Metals, what do they do with the electrons? So if you think of a typical metal, magnesium. Magnesium is found in group 2. Magnesium is in group 2, it's a metal. It's in group 2, so it has 2 valence electrons. So what does magnesium do during a reaction? During a chemical reaction, magnesium metal will lose electrons. Specifically, it loses its 2 valence electrons for magnesium. And when you lose valence electrons, what kind of ions do you form? So if you think of magnesium again, magnesium loses 2 valence electrons. It becomes Mg2+. So the idea is it forms positive ions. All right, so metals lose electrons to form positive ions. Okay. The reverse, non-metals will therefore gain electrons to form negative ions. The way to remember this is electrons are negative. If you gain more electrons, this means that overall your charge will be negative. So a good example would be, let's say, oxygen. Oxygen has 6 valence electrons, meaning it will gain 2 valence electrons to form O2 minus ion. Okay? Now, how is this relevant? Now, this is relevant to the periodic table. As we go from left to right, left to right means from group 1 all the way to the other side. You can see that the number of valence electrons, what happens? As you go from left to right, group 1, sodium, 1 valence electron. Group 2, magnesium, 2 valence electrons. You move on, you realize the number of electrons in the outer shell increases. Right? At the same time, what happens to the proton number as well? As you go from left to right, let's say sodium all the way to chlorine. Sodium to chlorine, I'm sure you can predict. If you look at the periodic table, the proton number also increases. What this means is that, hey, now you have more protons to attract the electrons. Hence, the tendency of the element to lose electrons, do you think the tendency will be higher as you move from left to right or lower to lose electrons? So if you think about it, as you go from left to right, the tendency of the element to lose electrons decreases. Meaning, lose electron, don't want to lose electrons. So who lose electrons? Metals lose electrons. So we know that metals lose electrons, therefore metallic character decreases. Okay? So I know this sounds very commonsensical, but the explanation, as you can see, is very much rooted in terms of electrons. And that's something that I think many students do overlook at times, right? So this is an important trend under the topic of periodic table, that metallic character decreases as you go from left to right. And this is the explanation in terms of electrons. All right, so let me pause the recording for a short while for you to take this down. So now that we have established that metallic character decreases as we go from left to right, if you look at the periodic table, the majority of elements are metals. And this is why studying the chapter of metals is important. And that's why you're given so much to learn in metals, this chapter. Now, the first thing you need to learn, of course, are the physical properties of metals. Now, physical properties have to do with things like electrical conductivity, thermal conductivity, hardness, strength, melting point. The first physical property that you should learn is that all metals are good conductors of electricity. There's no exception to this. So long as it's a metal, it will be a good conductor of electricity. The next physical property, all metals are good conductors of heat. So again, there is no exception to this. You have noticed that I've deliberately written the all there. This is because for these two physical properties, it applies to all metals. The next physical properties that I will talk about do have some exceptions, meaning some metals may not follow that physical property. And I'm referring to melting point. Metals generally have a high melting and boiling point. So generally speaking, metals should melt at a high temperature. However, you notice that for this property, I wrote there generally. Generally means most. However, there are exceptions, and you need to know the exceptions. The exceptions are group 1. So your group 1 metals, sodium, potassium. Sodium and potassium have a relatively low melting point. Take, for example, potassium. Potassium melts at 63 degrees Celsius. All right. This means that I just need to warm potassium up slightly, it will melt. Okay. Compare that to iron. Iron melts at over 1,500 degrees Celsius. So iron has a much, much higher melting point compared to potassium metal. Besides, group 1, mercury. Mercury has a chemical symbol Hg. It is in the center block of metals called the transition metals. Now, mercury is a liquid at room temperature. Well, that's interesting, right? Because if it's a liquid at room temperature, that means the melting point of mercury is quite low. Okay? Now, mercury used to be used inside a thermometer. It's the liquid inside the thermometer in the past. This is because mercury expands and contracts in a uniform manner, allowing you to measure temperature as it expands or contracts. Okay? Now, mercury is a liquid at room temperature. In the entire periodic table, there are only 2 elements which are liquids at room temperature. One of them is mercury, and the other element is a non-metal. The other element that is a non-metal, that is a liquid, is bromine. Bromine is also a liquid at room temperature. All right? Okay? So for this property, there is an exception. So you have to know. All right? So these are the 3 main physical properties of metals. The next physical property is again specific to pure metals. Pure metals are malleable and ductile. And this is where you absolutely need to actually understand what is the meaning of these 2 words. They are similar, but not exactly the same. Malleable starts with M, right? So the idea is it can be molded into different shapes without breaking. So just yesterday, we did this question in class where we had the paper clip example. To make a paper clip, the metal has to be malleable because it needs to be molded into the shape of a paper clip. At the same time, when you push paper into the paper clip must bend into a different shape without breaking. So pure metals can fulfill this function because it's malleable. Ductile. Ductile has a similar meaning, but ductile is specific. It can be pulled into thin wires without breaking. So ductile is more to do with pulling it as opposed to twisting it. All right. So pure metals are malleable and ductile. You notice I've said pure metals over here. This means that I'm looking at the metal on its own. It's not mixed with something else. All right. So this concludes the 4 physical properties of metals. Do take note. Points number 1 and 2 are common for all metals. Point number 3, high melting point, is only for most metals. So group 1 metals and mercury have a low melting point. Finally, please also take note what's the meaning of the word malleable and ductile. All right, let me pause the recording for a short while for you to take down this. Now that we have learned the physical properties of metals, let's think about them. Okay, so metals are good conductors of electricity. That means they can be used in electrical circuits. Good conductors of heat means they can be used to make, let's say, pots and pans so that your food will heat up faster. High melting point. This means that metals can be used to make containers to withstand heat, and that's important especially if you have a chemical reaction that's exothermic, it releases so much heat, right? So the container must be able to withstand the high temperature. But we come to this point about pure metals are malleable and ductile. We seem to think that that's a good thing, right? If you can twist them, mold them, or pull them into a different shape. However, that may not be a good thing. Because if the metal is so easily twisted and deformed, it may mean that it lacks strength. So pure metals, unfortunately, they are not very strong materials. As a result, you will need to use alloys. So I think we came across this word yesterday. So do you recall what is the meaning of the word alloy? Okay, what is the definition of an alloy? So an alloy is a mixture. What is it a mixture of? What does it contain? This is a mixture of a metal with other elements, right? So it contains one metal at least with other elements. The other elements can be metallic or non-metallic. Okay? Now the keyword here really is mixture. So this brings back the previous topics called elements, compounds, and mixtures. So metals that are pure are elements, metallic elements. But alloys are not elements. Alloys are mixtures. What does that mean? It means that they are impure. Mixtures are by definition impure. And how do you actually prove that they are impure? To prove whether something is pure or impure, we look at its melting and boiling point. So we realize that for alloys, they will melt and boil over a range of temperatures. That means if you were to try to melt an alloy, it may start melting at 1000 degrees and continue melting until 1050 degrees. The melting takes place over a range of temperature values. Now, this is a telltale indicative proof that this substance is impure, because pure substances should have a fixed melting and fixed boiling point. So mixtures have no fixed melting point and boiling point. Okay. Now this comes out very often as an MCQ for O levels. They will always ask you, which experiment proves that this substance is pure? It's pure if the melting point is fixed. It's impure if the melting point is not fixed and it melts over a range of temperatures. So purity is always determined by the melting and boiling points. Next, if it's a mixture, besides saying that it's impure, another important concept here is that the components of the mixture, they are not chemically combined in a fixed ratio. Okay, I'm sure you have learned this phrase before, not chemically combined in a fixed ratio. But what does it mean? For instance, if you say an alloy, this alloy contains iron and carbon, let's say. Must the iron and carbon be in a 90% to 10% ratio? No. To make the alloy, I could have used 90% iron, 10% carbon. I could also have used 99% iron, 1% carbon. There is really no fixed ratio of the components in an alloy. And because there's no fixed ratio, there is no chemical formula. If you notice, you have written chemical formulas so many times, But have you written a chemical formula for a mixture? The answer is no, you can't. Because the components are not in any fixed ratio. Okay? Now, so these are the important things you need to know. The next thing you need to know is the examples of alloys. The best example is steel. Steel is an alloy containing iron and carbon. So you notice, do the elements present in an alloy have to be metals? Must they all be metals? The answer is no. Steel is an alloy of iron. It contains the metal iron mixed with carbon. Right? Carbon is metal. Okay? So alloys can have metal and non-metal mixed together. Need not all be metals. Now, related to steel is another alloy called stainless steel. This one you must know. So please write down the elements. It contains iron and carbon, just like steel. It contains another important element, chromium. Okay, you can remember as IC. Iron, carbon, chromium. Now, the chromium is the one that's very important. Okay, now, before we get to why chromium is important, we should know why we use stainless steel. Stainless steel is resistant to rusting or corrosion. That means stainless steel will not form rust, which is important because sometimes you do not want your materials to rust. So what makes stainless steel resistant to rusting is this element called chromium. Now, chromium is a metal. Okay? Chromium is another metal. And this reacts with oxygen in the air. So chromium reacts with oxygen in the air. When it reacts, it forms chromium trioxide. Okay, so now let's try to work out the chemical formula of chromium trioxide. Okay, chromium's chemical symbol is Cr. So let's all work out the formula of chromium trioxide. So for those watching the video, maybe you like to pause the video to like work it out. Okay, so I hope everyone has figured it out. Okay, formula is Cr2O3. Now, what's so magical about this? It's magical because it forms a protective layer around the iron that prevents it from coming into contact with oxygen or water. So what you have is a piece of iron which is now surrounded by a layer of Cr2O3. All right? And this prevents the iron from coming into contact with oxygen or water. Therefore, it doesn't rust because you need oxygen or water for rusting to take place. Right? So this is how stainless steel works. And stainless steel is an alloy. It's a mixture of iron, carbon, and chromium. Now, the iron, carbon, and chromium may not be in a fixed ratio, right? So depending on what kind of stainless steel you are making, you may actually use more chromium or less chromium. You may actually use more carbon or less carbon. All right. Now, another two important alloys, rust, is copper and zinc. So this is an alloy of two metals, copper and zinc. Bronze, copper, and tin. Tin is another metal. All right. Now, someone asked whether the chromium oxide layer can break. Now, the chromium oxide layer, yes, it can be broken but the chromium immediately reacts with oxygen again to form more chromium oxide. So effectively, the chromium oxide layer does not get depleted. It does not get destroyed, because if you try to destroy a little bit of it, the chromium will react immediately with oxygen to form chromium 3 oxide. All right. And now that I've said that, I'm sure you can predict which is the more reactive metal, iron or chromium. I'm sure you can work out. Chromium is actually more reactive than iron. That's why chromium reacts with oxygen faster than iron can react with oxygen. Okay. Now, these are the 4 examples of alloys that I think you should know. Okay. Now, we come to the final point, which is alloys. So why are the alloys so useful? Besides stainless steel is resistant to rusting, but besides stainless steel, the other alloys like steel, bronze, they are used because alloys are harder and stronger than the pure metals. So alloys are harder and stronger than pure metals will be. And you need to now know why. Okay, so this is where, okay, when we were teaching our students, we always teach them the 3Ds. What are the 3Ds? First thing is the atoms in an alloy are of different sizes. That's, of course, a consequence of it being a mixture. It's a mixture of metal with other elements. So, of course, it has different types of atoms, and each atom has its own size, right? Iron atoms are of certain size. Carbon atoms, different size. So, that's the first D, different size. The second D, when you have different sizes, it disrupts the regular layered arrangement of atoms. Typically, in a metal, the atoms are arranged in regular, neat layers. But if the atoms are of different sizes, it will disrupt, okay, the regular layered arrangement. Therefore, the last D already, it is more difficult for the layers of atoms to slide past one another easily when a force is applied. Right? So the idea is it's stronger because the layers don't slide past each other so easily. Right? So the 3Ds, different size, disrupting the regular layer arrangement of atoms, difficult for the layers to slide over one another or slide past one another. Okay, so this is the main reason why alloys are harder and stronger than pure metals. And because of this, alloys are widely used. They are widely used in construction. They are widely used in making objects as well, because you do not want your objects to be deformed so easily. Okay, so let's pause the recording for a short while for you to take this down before we move on to chemical reactivity series of metals. Okay, so moving on from the physical properties of metals, such as melting points, such as the hardness and the strength, now we go on to the chemical reactions. Chemical reactions of metals. You need to know the reactions with water, and sometimes we like to say cold water, steam, and finally acid. Now, under acid, we are actually going to use HCl, hydrochloric acid, as the main example. All right? Now, we shall come back to this in a very short while, okay? But just take note, we are studying the 3 different reactions of metals: metal plus water, metal plus steam, metal plus HCl. All right, we'll come back to this in a very short while. But the first question we need to answer is, do metals all have the same reactivity? And I think you already know by now the answer is no. Okay, metals all have different reactivities. All right. Now, this allows us to rank the metals in a reactivity series. So the reactivity series, which I'm going to write, and it will be in chemical symbols, starts with potassium. Potassium right at the top is the most reactive, followed by sodium, calcium, magnesium. All right. Then you have aluminium, which is just for your knowledge. Okay, combined science, actually, you don't have to know aluminium. I'm telling you, aluminium is there. And then you have carbon. Now, carbon is not a metal, but we still place it into the reactivity series for a reason, which we will see tomorrow during the lesson when we go through metals part 2. All right, but carbon is below aluminium. All right, and then immediately below carbon, we have zinc, iron, lead, and after that, hydrogen. So again, hydrogen is clearly a non-metal, but we still put it into the series because there is a reason for that, which we will see very, very shortly. And finally, copper, silver, gold. So Au is gold. Let's write it down in case you didn't know this, the chemical symbol. Right, so gold is the least reactive in this series at least. Of course, does this represent all the metals? Of course not. I just told you, right, there are 80 plus different metals in the periodic table. However, these are the most common metals, the common metals that we study. Okay? Okay? So this is the reactivity series. Now you can remember it as fleas, sand, cats, monkeys, and cute zebras in large heated cages soon. Sadly, gold didn't make it into the acronym. All right, but this is a good mnemonic to remember. Potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, lead, hydrogen, copper, silver. All right, so this is one way to remember. Please send cats, monkeys, and cute zebras in large heated cages soon. Okay, and so no matter which mnemonic you use, at the end of the day, you must remember the series. Okay, in this order. Remembering the series is very, very important. All right, because the series is not given to you in an exam. Okay, and also you need this series to work out which metals will react with water, which ones will react with steam, and which ones react with acid. And so now, if you have a highlighter, strongly advise you to use a highlighter, and we are going to do some highlighting. So first, the metals that react with water are the first 4. The first 4 react with cold water. That means potassium, sodium, calcium, magnesium. These are the ones that react with cold water. And then take a different highlighter if you have different highlighter. If not, just use a different colored pen. Up to iron. So from potassium up to iron, these react with steam. That means iron is the last metal to react with steam. And finally, take a different highlighter. It comes good. Everything up to lead. And this one will react with acids. Okay, so you need to know which metals react with what first and foremost before you delve into each equation to learn how do they react. All right, so let me give you some time to digest that and make sure you have highlighted the correct metals. Okay, so now that we are ready to move on, you have already highlighted which metals react with cold water, steam, and acids. Let's start with the first reaction. When metals react with cold water, metal plus cold water, it forms the metal hydroxide plus hydrogen gas. Right? Metal plus cold water will form the metal hydroxide. This is very crucial. Okay? So now we are going to be looking at the reaction with cold water. So which metals are able to react with cold water? It's only the top 4 most reactive. So we start off with potassium. Potassium is the most reactive in the series, so it reacts with cold water. Potassium reacts very violently with cold water. All right, it's very, very violent. And what does it form? As mentioned, it forms the metal hydroxide. So if it forms the metal hydroxide, in this case, it will be potassium hydroxide, which has the formula KOH. All right. And hydrogen gas. All right. Now, this reaction is so violent, the hydrogen gas catches fire and explodes. All right. That's the concept. Okay, so violent, the hydrogen gas would explode. Moreover, because you are forming potassium hydroxide, so you have also learned under acids and bases, potassium hydroxide solution is an example of a strong alkali. So potassium hydroxide has a pH of around 13 to 14. So we can say that the resulting KOH solution turns universal indicator purple. And then you write the equation, okay, with state symbols. This equation is not balanced yet. You will need to balance the equation yourself, right? But for today, I will do it for you. Okay, please practice balancing the equation yourself. Now, to balance the equation, obviously, you need to consider how many hydrogens do you have on the right versus the left. Quite immediately, you realize, okay, I don't have enough hydrogens on the left. So I need 2 H2O to balance the equation. But the moment I have 2 H2O, it means now I have 2 oxygens on the left. If you have 2 oxygens on the left, you must also have 2 oxygens on the right. So it's 2 KOH on the right to make 2 oxygen. If you have 2 KOH, you also need 2 potassiums on the left. So this is how you balance the equation. And this is how you get a good 3 to 5 marks for describing the reaction of potassium with cold water. So you need to get to this level of detail when you describe a reaction. How violent is it? Does the gas explode? The resulting solution, if it's alkaline, you will need to address it. All right. In this case, it is strongly alkaline. Therefore, it will turn universal indicator purple. All right. So that's for potassium. Now, we will go on to the other metals, but I won't go through all of them in this level of detail. Okay, but I'll just bring you quickly through them. All right. The next metal is, of course, sodium. Now, sodium is less reactive than potassium because sodium is actually lower in the reactivity series. If you are lower in the series, you are less reactive. All right. Now, because you're less reactive, sodium is not very violent. Sodium is just violence with cold water. All right. It reacts violently with cold water to form sodium hydroxide and hydrogen gas. So the metal hydroxide is sodium hydroxide. All right. Now, this time round, the hydrogen gas produced is not so rapid. It's not as produced as rapidly as potassium. So the hydrogen gas may catch fire and explode. Right? So it may catch fire and explode. It's not definite, right? And of course, sodium hydroxide is one of the alkalis you always use for QA in the lab. So the resulting sodium hydroxide also has a pH of 14, so it turns universal indicator purple. All right. And how do you write the equation? Thankfully, sodium and potassium are both in group 1. And hence, the equations for sodium and potassium can be balanced in the same way. Meaning, it's almost the same equation, just that K is replaced by Na. Okay? Now, if you have done the prelim papers, you would have seen that, hey, or the TYS, you would have seen that, hey, many questions are like, describe the reaction of blah, blah, blah with water. And this is the level of detail that you need to get to. Writing a one-liner, writing the equation alone is not going to get you the full marks. This is the level of detail that you must address. What does it form? How violent is it? And finally, if it's alkaline, what is the result if you were to add universal indicator? All right, so let me pause the recording for a short while so that at least you can have time to copy down the reactions of potassium and sodium with cold water. Okay, so now that we have covered sodium, the next one in line is, of course, calcium. Okay. Now I'm going to use a different color, but you don't have to use a different color. Now, what's after violet? So calcium reacts moderately. So we go from very violent to violent and then moderate. So calcium reacts moderately with cold water. What does it form? It forms the metal hydroxide. But what's the formula? In this case, it's calcium hydroxide. So now you have to think. Calcium is not in the same group as potassium and sodium. Potassium and sodium was in group 1. Calcium is in group number 2. And therefore, calcium has 2 valence electrons. It will form Ca2+. As a result of that, calcium hydroxide's formula is not CaOH. It's not this. It has to be CaOH2. All right, so it forms calcium hydroxide, Ca bracket OH2, and hydrogen gas. Okay, now the hydrogen gas produced is not produced that rapidly, and therefore you don't even see the hydrogen gas catching fire. All right, now, so there's no catching fire when calcium reacts with cold water. However, the resulting calcium hydroxide solution, calcium hydroxide is not a strong alkali. It's not as strong as sodium and potassium hydroxides. Therefore, the resulting calcium hydroxide solution only has a pH of around 11. And so it turns universal indicator blue. It will not turn the resulting solution purple. All right. Okay, so there's a big difference between calcium and sodium. Next, trying to balance this equation again. have to write out the equation with state symbols. All right, this is not balanced yet. You need to balance this equation. All right, immediately you realize, oh, well, I can clearly see O got two of it because it's bracket OH2. So on the right-hand side, you have two oxygens. There is only one oxygen on the left. Therefore, we put a 2 in front of the H2O. So it's Ca plus 2H2O becomes CaOH2 and H2. Okay, now this is already a balanced equation. You can try counting the other elements like calcium and hydrogen. You realize that it's completely balanced. All right. Can so far you realize that, oh, still quite similar, just that the formula are different because calcium is from group number 2. Next, you realize that group 2 elements are actually less reactive than group 1 elements. Group 1 metals, potassium, sodium, they are very, very reactive. Group 2, calcium, magnesium, less reactive, but still reactive. Now, finally, we come to the last one, which is magnesium. Another group 2 element. So we have had very violently, then moderately. The last one, slowly. All right. Now, okay, besides moderately, okay, maybe I should address besides moderately, we could have said readily. Another word is readily, yes. Right, another word for moderately is readily. Okay. So magnesium reacts slowly with cold water. So is this hierarchy, very violently, readily or moderately, then slowly. It's the last one. Now, what does it form? It forms magnesium hydroxide and hydrogen gas. Now, as similar to calcium, magnesium is in group 2, therefore, it will form Mg2+. Hence, the formula is Mg bracket OH2. Okay? Now, how slow is slow? If you collected the hydrogen, a tube of hydrogen gas is collected after a few days. The production of hydrogen is so slow, it takes days for a tube of hydrogen gas to be collected. And besides that, unlike potassium, calcium, and sodium hydroxides, the magnesium hydroxide is formed not as a solution. It's formed as an insoluble precipitate. An insoluble precipitate of magnesium hydroxide is formed. Now, magnesium hydroxide is insoluble in water. All right? Which means now, your equation will have to change. How does it change? The state symbols change. All right? You can see that magnesium hydroxide is now produced as a solid instead of aqueous. All right? So the magnesium hydroxide is produced as a solid, so you have to reflect that in the state symbol. It's a solid. And obviously, if it's produced as an insoluble precipitate, it will not change the color of your litmus paper. It will not change the color of universal indicator. All right? So magnesium hydroxide, even though it's a base, it's not an alkali because it doesn't dissolve in water. If it doesn't dissolve in water, it doesn't change the color of litmus paper or doesn't change the color of universal indicator. Okay? So these are the 4 reactions, all right, present for the 4 metals which react with water. Okay? And this is the level to which you are supposed to explain in the exam. All right? So that concludes, okay, I think we should conclude our lesson here. Tomorrow, we will continue with the reactions of metals with steam, with hydrochloric acid, as well as go through displacement reactions of metals and link that to redox, as we did a little bit of, as we did the prelim papers in class today. All right, so let me just stop the recording now. Okay, thank you.